November 15, 1943. Aberdeen, Proving Ground, Maryland. 34 degrees and falling. A lone German Kübelwagen rests on American soil. 1,740 pounds of enemy ingenuity, which every mechanic anticipates will be a marvel of automotive design. Staff Sergeant Mike Kowalski, 15 years of Detroit assembly line expertise in his hands, observes as the Wehrmacht's answer to the American Jeep is unloaded from a transport truck. This is no ordinary captured vehicle. This is supposed to represent the pinnacle of German engineering on 4 wheels. The High Command is demanding a comprehensive technical assessment. Every American mechanic holds the belief that the Germans fabricate the finest automobiles globally. Kowalski lifts the hood for his initial inspection. What he beholds freezes him in his tracks. A diminutive air-cooled engine that resembles a lawnmower motor more than military hardware. He verifies the specifications a second time. 25 horsepower. The American Willys Jeep generates 60. This German wonder weapon possesses less power than a 1920 Ford Model A. Yet, if German engineering isn't superior, then why are American GIs perishing in the European mire? The transport truck's diesel engine coughed to a halt as Staff Sergeant Mike Kowalski pulled his collar tighter against the November chill. Aberdeen Proving Ground sprawled across Maryland's frozen terrain like a vast mechanical necropolis, strewn with the skeletal remains of tanks, trucks, and artillery pieces that had succumbed to America's rigorous testing protocols. Today's delivery was unique. Today, they were unveiling German engineering. The Kübelwagen emerged from beneath its olive-drab tarp as if it were a revelation. Kowalski had seen the intelligence photographs, absorbed the War Department briefings, and studied the tactical reports from North Africa. This was Volkswagen's military magnum opus, the vehicle that had conveyed Wehrmacht officers across a conquered Europe, the automotive embodiment of German precision engineering. Even stationary on Aberdeen's concrete pad, it exuded an undeniable grace that rendered the nearby American Jeeps crude by comparison. Technical Sergeant James Patterson approached from the dynamometer building, his breath misting in the frigid air as he carried a clipboard laden with testing procedures. 5 years at General Motors had instilled in him a methodical precision for every vehicle evaluation. But even he could not conceal his intrigue regarding this particular specimen. "The War Department wants the full treatment," he announced, his voice carrying the authority of one who had translated Detroit's engineering standards into military parlance. "Complete technical analysis for manual TME 983. Everything from power curves to maintenance requirements." Kowalski nodded, his calloused hands already reaching for the hood release. 15 years on Ford and Chrysler assembly lines had bestowed upon him an intuitive grasp of automotive engineering that surpassed formal education. He could diagnose transmission issues by the sound of gear changes, identify bearing failures through subtle vibrations imperceptible to others. The Kübelwagen represented more than just another testing assignment. It was his opportunity to gauge America's industrial might against the fabled German engineering tradition. The hood lifted with a satisfying mechanical click, exposing the engine compartment in all its Teutonic splendor. Kowalski gazed for an extended moment, his expression transitioning from anticipation to bewilderment. The power plant nestled between the frame rails appeared more akin to something from a civilian economy car than a military vehicle. Air-cooled cylinders arranged horizontally, minimalist in their construction, almost delicate when contrasted with the robust cast-iron blocks he knew from Detroit. 25 horsepower, he murmured, reconfirming the specifications clipped to Patterson's board. The numbers were irrefutable, yet they defied comprehension. The American Willys Jeep, parked 50 yards distant, produced 60 horsepower from its Willys Go Devil engine, more than double the output of this German machine. Even the venerable Ford Model A his father had driven in the 1920s generated more power than this supposed wonder weapon. Corporal Tommy Chen appeared beside them, his slide rule already in hand with the practiced efficiency of a Berkeley engineering student. Mathematics was Chen's native tongue, and he approached every problem through the prism of quantifiable relationships. Displacement 985 cubic centimeters, he announced, his calculations translating German specifications into figures comprehensible to American mechanics. That's approximately 60 cubic inches, peak power at 3,300 RPM. His slide rule moved with practiced alacrity, converting metric measurements into familiar imperial units. Power to displacement ratio is terrible, worse than most civilian vehicles. Patterson meticulously recorded notes. His engineering background demanded documentation of every observation. This was not merely mechanical curiosity. The War Department required comprehensive data on enemy equipment capabilities. American commanders were making tactical decisions based on assumptions of German technical superiority. If those assumptions were flawed, the implications extended far beyond automotive engineering. Major Robert Sterling arrived as the team commenced their preliminary inspection, his press uniform adorned with polished brass, marking him as a representative of the institutional military establishment. 20 years of service had taught him to respect European military traditions, and his West Point education had underscored the importance of understanding enemy capabilities. "Gentlemen," he announced with formal courtesy, "this evaluation carries significant strategic importance. German automotive engineering has long been considered among the world's finest. We need to ascertain precisely what advantages their equipment affords." Kowalski suppressed his immediate response. Years of military discipline overruled his working-class instincts. The Major's expectations were clear. They were expected to discover evidence of German technical superiority, to quantify the engineering advantages that accounted for Wehrmacht battlefield successes. However, the evidence before them told a decidedly different narrative. The engine's construction revealed design choices that prioritized different values than American automotive engineering. Where Detroit engineered for power and endurance, the Germans had optimized for fuel efficiency and manufacturing simplicity. The air cooling system eliminated the weight and complexity of liquid cooling, but at the cost of thermal management under duress. The rear-mounted configuration enhanced traction in snow and mud, but created maintenance access challenges that would vex field mechanics. As the afternoon shadows lengthened across Aberdeen's testing grounds, Kowalski found himself contemplating a machine that challenged his every belief about German engineering supremacy. This was not the automotive masterpiece suggested by intelligence reports. It was a compromise, elegant in certain aspects, yet fundamentally constrained by design decisions that favored theory over practical battlefield performance. The true testing would commence tomorrow, when dynamometer readings would supplant subjective impressions with concrete figures. Yet, even now, Kowalski sensed they were on the verge of uncovering something that would profoundly shake the War Department's foundational assumptions about enemy capabilities. The Emperor's new automobile sat before them, awaiting comparison with the unglamorous yet potent reality of American industrial engineering. The dynamometer building hummed with electrical energy as Technical Sergeant Patterson activated the immense testing apparatus designed to measure the Kübelwagen's actual performance against its advertised specifications. 4 days of preparation had transformed Aberdeen's primary automotive testing facility into a precision measurement laboratory, with cables snaking across the concrete floor like mechanical arteries, linking German engineering to American scientific methodology. Kowalski guided the Kübelwagen onto the dynamometer rollers with practiced exactitude, feeling the vehicle settle into the testing cradle that would hold it immobile while its wheels spun against calibrated resistance. The morning air carried the sharp aroma of industrial lubricants and electrical equipment, familiar scents that conjured memories of Detroit's proving grounds where peacetime automotive dreams had once been measured against mathematical reality. Initiating baseline power measurement, Patterson announced, his voice resonating with the methodical tone of someone who understood that imprecise data undermined credible conclusions. 5 years of General Motors engineering discipline had ingrained in him a commitment to laboratory precision, meticulously documenting variables that less experienced technicians might overlook. The War Department demanded figures that could withstand scrutiny from Pentagon engineers who, though lacking combat experience, possessed unwavering faith in quantified analysis. The Kübelwagen's engine note shifted as Patterson gradually increased the dynamometer load, simulating the resistance of inclines, headwinds, and battlefield conditions that would challenge the vehicle's capabilities. At idle, the flat-4 engine produced a distinctive sound, smoother than American inline configurations, but somehow less substantial, akin to a sewing machine compared to a bulldozer. The air cooling system's fan emitted a constant whisper, seeming almost apologetic against the confident rumble of liquid-cooled American engines. Chen positioned himself beside the instrument panel, slide rule at the ready. His Berkeley engineering education provided the mathematical framework necessary to translate raw measurements into meaningful comparisons. Numbers represented truth in its purest form, impervious to propaganda, cultural bias, or wishful thinking. Peak torque at 2,400 RPM, he called out, recording figures destined for classified reports to Washington. Maximum power output, 25.3 horsepower at 3,300 revolutions per minute. The implications struck Kowalski with the force of cold water. These were not preliminary estimates or rough approximations. They were precise measurements of German automotive engineering at its theoretical apex. The Kübelwagen was performing precisely as designed, delivering every horsepower Volkswagen's engineers had promised. The issue was not mechanical failure or poor maintenance. The problem lay in German engineering's prioritization of entirely different objectives compared to American automotive design. Patterson's stopwatch clicked as they commenced acceleration tests, timing the Kübelwagen's progress from 0 to 30 miles per hour. 26 seconds elapsed before the speedometer needle reached the target velocity, a performance that would have been embarrassing for a civilian passenger car, let alone a military vehicle intended for battlefield mobility. The nearby Willys Jeep could complete the same acceleration test in 11 seconds, reaching 30 miles per hour with an authority that spoke volumes of Detroit's dedication to raw mechanical power. Weight comparison reveals interesting trade-offs, Chen announced, his calculations illuminating the engineering philosophy underpinning German design choices. Kübelwagen weighs 1,740 pounds versus the Jeep's 2,453 pounds. They save 700 pounds of structural mass, but the power-to-weight ratio still favors American engineering by a significant margin. Major Sterling observed from the building's observation deck, his military bearing unable to completely mask a growing unease regarding what these measurements indicated about enemy capabilities. 2 decades of service had conditioned him to respect European military traditions, but the numbers emerging from Aberdeen's testing facility challenged fundamental assumptions about German technical superiority. If Wehrmacht vehicles possessed inferior performance characteristics, how did German forces maintain tactical advantages across multiple theaters of operation? The transmission testing yielded further surprises as Patterson shifted through the Kübelwagen's 4 forward gears, measuring torque multiplication and mechanical efficiency at each ratio. German engineering had prioritized smoothness over robustness, creating a transmission that shifted with butter-soft precision but lacked the mechanical fortitude that American designers deemed essential for military application. The synchronized gear engagement felt almost delicate compared to the positive mechanical certainty of American transmissions, engineered for abuse by 19-year-old drivers under combat stress. Kowalski found himself contemplating the Wehrmacht mechanics who maintained these vehicles under battlefield conditions. His 15 years of assembly line experience had taught him that elegance was meaningless if it could not withstand real-world abuse. The Kübelwagen's sophisticated engineering would become a liability when overworked field mechanics were forced to perform repairs with improvised tools under artillery fire. The cooling system evaluation produced the most disquieting results of the entire testing sequence. Patterson monitored engine temperatures as the dynamometer load increased, observing coolant temperatures that would have mandated immediate shutdown procedures for any liquid-cooled American engine. The air cooling system's limitations became evident under sustained high-power output. Thermal management that performed adequately under normal civilian driving conditions began to falter when military demands necessitated continuous high-stress operation. Temperature rising beyond acceptable parameters at sustained 22 horsepower output, Patterson reported, his engineering background providing context for measurements that revealed fundamental design deficiencies. Thermal stress indicators suggest this power plant cannot maintain military performance standards under combat loading conditions. Chen's slide rule moved with practiced efficiency as he calculated thermal efficiency ratios and compared German air cooling performance against American liquid-cooled systems. The mathematics unveiled uncomfortable truths about engineering compromises that appeared elegant on paper but proved inadequate under battlefield stress. Heat dissipation inadequate for sustained military operation, he concluded, his figures corroborating what Kowalski's mechanical instincts had already discerned. As the morning's testing concluded, Kowalski gazed at the instrument readings that would soon be disseminated to Pentagon briefing rooms, where strategic decisions were formulated based on enemy capability assessments. Every number told the same story. American automotive engineering had achieved superior performance through a different design philosophy, prioritizing power and durability over theoretical elegance. The implications extended far beyond mechanical specifications, touching upon the very reasons why American soldiers were struggling against adversaries equipped with demonstrably inferior material. Aberdeen's hill-climbing course traversed the proving ground's eastern sector like a geometric challenge to automotive engineering. Its 12-degree gradient represented the kind of terrain that differentiated capable military vehicles from automotive pretenders. The morning air carried frost that would soon yield to the mechanical heat of engines pushed beyond their comfort zones. As Kowalski prepared to subject the Kübelwagen to tests that would reveal whether German engineering could translate theoretical horsepower into practical battlefield mobility, the course began with a quarter-mile approach, allowing vehicles to build momentum before encountering the gradient's steepest section, where incline physics would strip away every advantage save raw mechanical power and thermal management. Patterson had strategically positioned temperature monitoring equipment along the route, establishing a comprehensive measurement system that would document precisely how German air cooling performed under sustained load conditions, simulating combat operations in mountainous terrain. Kowalski engaged first gear and felt the Kübelwagen commence its assault on Aberdeen's artificial mountain. The flat four-engine's note shifted from a conversational idle to a labored protest as gradient physics demanded more power than Volkswagen's engineers had supplied. At the 500-foot mark, engine temperature gauges began registering thermal stress that would have triggered warning protocols in any liquid-cooled American vehicle. The air cooling system's fan whined with mechanical desperation, attempting to dissipate heat that accumulated faster than aluminum fins could release it to Maryland's cold November atmosphere. Chen monitored the vehicle's progress through binoculars, his slide rule calculating real-time power requirements against observed performance degradation. Mathematics revealed the brutal efficiency of physics. Every degree of incline exponentially multiplied the engine's workload, transforming the Kübelwagen's marginal 25 horsepower into woefully insufficient motivation for ascending even modest hills under load. "Speed dropping below 15 miles per hour," he called out, his voice carrying across the testing ground with clinical precision. Engine temperature exceeding normal operating parameters. The Kübelwagen's transmission began hunting between second and third gear as Kowalski struggled to maintain forward momentum against gravity's relentless mathematical certainty. German engineering had optimized for fuel efficiency and manufacturing simplicity, but battlefield mobility necessitated sustained power output that the air-cooled engine simply could not deliver without thermal distress. At the 800-foot mark, coolant temperature indicators entered the danger zone, where mechanical failure became inevitable rather than merely possible. Patterson's radio crackled with readings that confirmed what Kowalski could feel through the steering wheel and accelerator pedal. The Kübelwagen was approaching the limits of its engineering envelope under conditions that American Jeeps routinely handled with mechanical confidence. Temperature now at 210 degrees Fahrenheit, Patterson reported, his engineering background providing context for numbers that represented the difference between theoretical capability and practical battlefield utility. Recommend immediate shutdown to prevent engine damage. But Kowalski pressed onward, understanding that this test represented more than automotive evaluation. It was measuring whether German engineering superiority was a reality or merely an assumption. The engine's mechanical protests grew more desperate as aluminum pistons expanded beyond design tolerances, creating clearances that reduced compression and further degraded power output. Steam began rising from the engine compartment as lubricating oil approached temperatures where molecular breakdown would obliterate the engine's ability to shield itself from friction. Major Stirling observed from the observation bunker as the vehicle, a symbol of German automotive achievement, struggled up a hill that delivery trucks ascended daily without mechanical distress. His military education had emphasized respect for European engineering traditions. Yet, the evidence unfolding before him challenged assumptions that had shaped American strategic thinking since the war's commencement. If German vehicles possessed such fundamental limitations, how had Wehrmacht forces attained tactical superiority across multiple theaters of operation? At 900 feet, the Kübelwagen finally capitulated to physics and engineering reality. Kowalski felt power output collapse as thermal stress overwhelmed the engine's capacity to convert fuel into mechanical motion, leaving him coasting backward down the hill. While German precision engineering vented superheated air through every available aperture, the vehicle that intelligence reports had characterized as militarily capable had failed a test representing routine battlefield requirements rather than extreme operational conditions. A comparative assessment with an American Willys Jeep offered a striking illustration of differing engineering philosophies and their tangible tactical consequences. The Jeep ascended the same 12-degree incline with a mechanical assurance that underscored Detroit's predisposition for abundant reserves and thermal regulation via liquid cooling systems engineered for enduring high-stress operations. Where the Kübelwagen faltered and ceased to function, the American vehicle ascended with ample power reserves, capable of tackling even more severe gradients when fully laden for combat. Chen's calculations illuminated the numerical realities underlying these observed performance discrepancies. The maximum sustainable incline for the German vehicle appeared to be 8 degrees under load. He presented his findings, which translated thermal limitations into strategic constraints that would impact battlefield mobility across European terrain. The American Jeep's capability extended to 27 degrees under identical loading conditions. This advantage in power-to-weight ratio directly translated into superior operational mobility. As the afternoon's evaluations continued, news of the Kübelwagen's inability to conquer the hill spread throughout Aberdeen's vast facility like mechanical rumor. Technicians from other testing units abandoned their tasks to observe German automotive engineering being systematically dissected by American evaluation protocols. The vehicle that propaganda had once lauded as a symbol of Teutonic technical preeminence sat cooling in Maryland's November air, its limitations exposed by objective mathematics that disregarded national pride or cultural assumptions. The traction testing delivered the final indignity as Kowalski maneuvered the rear-wheel drive Kübelwagen into Aberdeen's sand trap, where controlled conditions would measure grip and mobility over terrain, simulating battlefield irregularities. 4 inches of loose sand, barely enough to challenge a standard passenger car, proved sufficient to completely incapacitate the German vehicle. Its narrow tires and rearward weight distribution created a combination that transformed minor obstacles into mission-ending mobility impediments. Patterson meticulously documented every measurement, understanding that these figures would be presented in Pentagon briefing rooms, influencing strategic decisions based on enemy capability assessments. The same sand trap that halted American Jeeps at 18 inches had defeated German engineering at a mere 4 inches, revealing design priorities that favored theoretical elegance over practical battlefield utility in scenarios representing routine military operations, not extreme tactical situations. Aberdeen's maintenance bay echoed with the precise sounds of systematic disassembly as Kowalski moved towards the final evaluation phase, which would determine if German engineering compensated for performance shortcomings with superior serviceability and battlefield maintenance characteristics. December's biting cold had transformed the unheated workshop into an environment simulating the harsh conditions where combat mechanics would struggle to keep vehicles operational under enemy fire and adverse weather. The routine oil change initiated what Patterson had termed comparative maintenance analysis, timing each procedure against identical operations on American equipment to quantify the hidden costs associated with design complexity. Kowalski's stopwatch began as he located the Kübelwagen's oil drain plug, immediately encountering the first indication that German engineers had prioritized theoretical elegance over practical field service. The drain point was situated behind a protective skid plate requiring tool access from multiple angles, turning a straightforward task into an exercise in mechanical contortion. 15 minutes have passed and we haven't drained a single drop, Kowalski grumbled, his breath visible in the frigid air as he wrestled with access panels that seemed designed by individuals who had never performed an oil change under combat conditions. 15 years of experience on Detroit assembly lines had taught him that maintenance complexity was the antithesis of operational availability. Every extra minute spent servicing vehicles represented time diverted from combat readiness and increased vulnerability to enemy actions. Patterson documented each step with methodical accuracy, understanding that these measurements would inform War Department maintenance protocols for captured enemy equipment. His General Motors engineering background provided context for design decisions that, while appearing sophisticated on technical drawings, presented practical nightmares for field mechanics working with limited tools in challenging environments. German design philosophy appears to favor component protection over service accessibility, he observed, watching Kowalski struggle with fasteners that required specialized tools rather than standard military wrenches. The oil change, which took 12 minutes on an American Jeep, required 45 minutes on the Kübelwagen, with the majority of the additional time spent accessing components that German engineers had concealed beneath protective covers and structural elements. Chen calculated the tactical implications with slide rule precision, translating maintenance time differences into operational availability statistics that revealed the hidden costs of engineering complexity. The maintenance time differential represents a 27% reduction in unit availability during sustained operations, he announced, his calculations illustrating how design choices impacted combat effectiveness through logistical constraints rather than mechanical performance. Spark plug replacement provided even more dramatic evidence of German engineering priorities that favored theoretical perfection over battlefield practicality. The Kübelwagen's horizontally opposed engine configuration buried the spark plugs beneath cooling shrouds and electrical components, necessitating partial engine disassembly for access. What should have been an 8-minute procedure on any standard military vehicle became a 35-minute expedition into mechanical archaeology, leaving Kowalski questioning the sanity of engineers who had never worked under artillery bombardment. "This is insane," he declared, holding a spark plug that had required the removal of 6 separate components to reach. Any farm mechanic in Iowa could service a Jeep engine with a basic toolkit. This thing requires a complete workshop and half a day just to change plugs. His working-class pragmatism recoiled against design complexity that served no practical purpose beyond showcasing engineering sophistication to individuals who would never be responsible for maintaining the equipment they created. Major Sterling observed the maintenance evaluation with growing comprehension of how engineering decisions influenced tactical capabilities through logistical, rather than performance, constraints. His military education had emphasized the critical importance of maintaining equipment operational under combat conditions. However, the evidence emerging from Aberdeen's workshop revealed fundamental differences in design philosophy that would determine battlefield effectiveness, irrespective of theoretical capabilities. How do German field units maintain operational readiness with these service requirements? He inquired, understanding that maintenance complexity represented a strategic vulnerability that Allied forces could exploit through sustained operations. The air filter service provided the final demonstration of German engineering priorities, transforming routine maintenance into significant mechanical undertakings. Accessing the filter element necessitated removing engine shrouds, disconnecting electrical cables, and partially dismantling the cooling system. This 25-minute procedure accomplished what American engineers had made possible in 3 minutes through design decisions that prioritized practical service over theoretical optimization. Patterson's documentation revealed patterns that extended beyond individual maintenance operations to encompass comprehensive differences in engineering philosophy between American and German automotive design. German engineers appear to have optimized for manufacturing efficiency and theoretical performance while accepting maintenance complexity as an acceptable trade-off, he concluded his analysis, revealing how design decisions made in peacetime engineering offices would impact battlefield operations under conditions the designers had never experienced. Chen's mathematical analysis converted individual maintenance time measurements into strategic assessments of logistical sustainability under combat conditions. Cumulative maintenance requirements would reduce German unit availability by approximately 30% compared to American equipment under identical operational tempos, he calculated. Understanding that these figures represented the difference between tactical success and logistical collapse during sustained military operations. The cold start testing on December 8th provided final confirmation of German engineering limitations that would prove devastating under actual combat conditions. At 10 degrees Fahrenheit, typical European winter weather, the Kübelwagen's engine refused to start despite 6 attempts following proper starting procedures. The air cooling system, which eliminated liquid coolant freeze-up issues, created carburation and ignition difficulties that rendered cold weather operation unreliable when battlefield conditions demanded absolute mechanical dependability. Kowalski watched the American Jeep fire up immediately under identical conditions. Its liquid-cooled engine and robust electrical system demonstrated design priorities that favored operational reliability over theoretical efficiency. "Game over," he declared, understanding that these measurements represented more than a simple automotive comparison. They signified an engineering philosophy that would determine which industrial system could sustain military operations under conditions where mechanical failure meant tactical defeat. As December's testing concluded, The maintenance evaluation had exposed German engineering limitations, extending far beyond horsepower specifications into operational sustainability under battlefield conditions. The Kübelwagen represented sophisticated engineering that met theoretical requirements while failing practical tests that determined military effectiveness and performance constraints. December 15th arrived at Aberdeen with a bitter cold that turned metal into ice and made every mechanical operation a test of human endurance as much as engineering capability. Kowalski sat in the empty maintenance bay, gazing at his completed technical report. Outside, the wind howled across Maryland's frozen landscape with the same relentless persistence that German forces were demonstrating across European battlefields, despite their demonstrably inferior equipment. Every figure in Technical Manual TME 983 told the same uncompromising story. American automotive engineering had achieved measurable superiority over German design in every category essential for military effectiveness. 25 horsepower versus 60, 45-minute oil changes versus 12 minutes, hill climbing failure at 8 degrees versus 27-degree capability. The mathematics were irrefutable, documented with scientific precision that would withstand scrutiny from Pentagon engineers who trusted numbers above propaganda or cultural assumptions. Yet, American soldiers were still dying in Italian mountains and French hedgerows, still locked in struggle against Wehrmacht forces equipped with vehicles that Aberdeen's testing had proven inferior to American industrial output. This contradiction gnawed at Kowalski's working-class logic like a mechanical problem resisting conventional diagnostic procedures. If German equipment was so inadequate, why weren't American forces achieving decisive victories instead of fighting yard by yard through terrain that seemed to favor defenders equipped with less capable materiel? Patterson found him there after midnight, the former General Motors engineer carrying 2 cups of coffee and the weight of his own professional confusion about the discrepancy between their testing results and battlefield reports indicating German tactical effectiveness. "Numbers don't lie," he said, settling into a chair beside the workbench where months of measurement data lay arranged in neat piles, representing the systematic dismantling of German engineering mythology. But they don't explain why Wehrmacht units maintain operational effectiveness despite the equipment limitations we've documented. The ensuing conversation would later be recalled as the moment when Aberdeen's testing team realized they had been posing the wrong questions about military effectiveness and technological superiority. Chen joined them around 3 in the morning, his slide rule forgotten, as mathematical precision gave way to a broader understanding of how warfare actually functioned when human factors combined with mechanical capabilities to produce tactical outcomes transcending simple equipment comparisons. "We've been measuring the wrong variables," Patterson stated. His engineering background provided a framework for an analysis that extended beyond horsepower specifications to encompass operational factors determining battlefield success. Regardless of theoretical equipment advantages, German forces aren't winning because their vehicles are better. They're winning despite having worse vehicles because of superior doctrine, training, and tactical integration that maximizes limited mechanical capabilities. This insight struck Kowalski with the force of mechanical revelation, transforming months of testing data from a confusing contradiction into a coherent explanation of how military effectiveness arose from complex interactions between equipment, training, tactics, and operational experience, rather than simple technological superiority. German units succeeded because they understood how to extract maximum capability from limited resources, while American forces were still learning how to integrate superior equipment into effective tactical systems. Major Sterling discovered them at dawn. 3 men surrounded by documentation that had evolved from a simple automotive evaluation into a strategic analysis of why equipment advantages did not automatically translate into battlefield success. His military education provided context for conclusions that challenged fundamental assumptions about technological determinism in warfare while revealing uncomfortable truths about American tactical doctrine, which emphasized material superiority over operational effectiveness. German engineering wasn't superior, Kowalski declared, articulating insights that months of systematic measurement of automotive reality versus cultural mythology had gradually revealed. It was just different, optimized for mass production under resource constraints rather than performance maximization. They're fighting a poor man's war with equipment designed for efficiency rather than capability. And they're winning because they understand how to use limited resources effectively. The implications extended far beyond Aberdeen's testing protocols into strategic questions about how American industrial might could be translated into tactical advantage on European battlefields, where German forces continued to demonstrate operational effectiveness despite material disadvantages that Aberdeen's testing had quantified with scientific precision. Superior equipment meant nothing if operators lacked the training, doctrine, or experience necessary to exploit technological advantages under combat conditions. Patterson began drafting supplementary analysis that would accompany Technical Manual TME 983 to Pentagon briefing rooms, explaining how German tactical success, despite equipment inferiority, highlighted the importance of training, doctrine, and operational experience in determining battlefield outcomes. American forces possessed superior vehicles, weapons, and logistical support, but German units maintained tactical effectiveness through superior integration of limited resources into coherent operational systems. Chen's mathematical models revealed the strategic implications of Aberdeen's discoveries, calculating how American equipment advantages would eventually overcome German tactical superiority as Allied forces gained operational experience, while Wehrmacht units exhausted their trained personnel and logistical infrastructure. The war would be won by industrial capacity rather than individual equipment superiority, with American mass production overwhelming German efficiency through sheer quantitative advantage. As morning light filtered through Aberdeen's windows, the team understood they had documented more than an automotive comparison. They had revealed fundamental differences between American and German approaches to military technology that would ultimately determine the war's outcome. German engineering represented sophisticated optimization under resource constraints, while American production demonstrated industrial capacity that could overwhelm efficiency through massive quantitative superiority. The final report emerging from Aberdeen's testing would travel to the European theater of operations as Technical Manual TME 983, carrying mathematical proof that American equipment was superior to German alternatives across every measurable category. But more importantly, it would explain why equipment superiority alone was insufficient for tactical success without proper doctrine, training, and operational integration that maximized technological advantages under battlefield conditions. On June 6, 1944, 16,000 American Jeeps rolled onto Norman beaches, carrying soldiers trained to exploit their equipment superiority through doctrine that had learned from German tactical success. Kowalski's technical manual provided mathematical confirmation of what D-Day would demonstrate operationally. American industrial might, properly applied through effective tactics, would prove decisive against German efficiency constrained by limited resources and increasingly desperate strategic circumstances that no amount of engineering sophistication could overcome.